All right, Stella, I'm ready for my beauty shot for the video. Okay, thank you. Okay, so this is the first video of the third packet, and we're learning about polynomial functions. All right, so basically, they're just functions, and the highest exponents will be bigger numbers than 2. Okay, so for most of this year, we've been working with quadratic functions, which is an example of a polynomial function. Okay, for quadratics, the highest exponent is 2. Okay, so basically now we're going to work with more terms, and the exponents can be higher than 2. All right, so just like quadratics, when we solve quadratics, we usually get 2 roots or 2 answers because the highest exponent is 2. This is also called the second degree polynomial. So we could have up to 2 roots. I should say up to 2 answers. All right, so sometimes those roots match. We have a double root, so really we only have one distinct answer. Okay, and there are different types of roots. Okay, we've learned about real and imaginary numbers. So when we have roots that are real, they will actually cross the x-axis. They're also called the y-intercepts. Okay, and I'm sorry, they're called the x-intercepts because they cross the x-axis. They're also called zeros. All right, if we have imaginary roots, they will not cross the x-axis. Okay, and imaginary roots always come in pairs. We'll talk about this later. Okay, so basically this next section, okay, even with this, is talking about what we call end behavior. It's just talking about the ends of the graphs. Okay, so we can have an even highest exponent, an even degree, or an odd degree. Okay, so anything like if we have x squareds or x to the fourth or x to the sixes, so on, any of the highest exponent is even, we're going to have the tails go in the same direction. So we're familiar with a second degree, a parabola. Okay, so this would be an x squared most likely, and the tails are both going up. If there's a negative leading coefficient, both tails are down. But if we have an even degree, the tails will always be in the same direction. All right, a fourth power might look like this. Okay, basically the higher the degree, the more potential there are for curves. Okay, so odd degree, tails would be in the opposite direction. Okay, this is a sketch of a cubic. Okay, this is the next to the third. And notice since we have an odd number as the highest degree, the tails, one goes down and one goes up. They go in opposite directions. So odd degree, if you flip the two D's around, you actually get the abbreviation for opposite. So odd degrees have opposite tails. That's something you can remember. All right. I mentioned the lead coefficient. Okay, the lead coefficient is positive. Okay, I'm just going to kind of go back up to this parabola that I drew. This would be an example of a positive ax squared. Okay, and this would be a negative ax squared that starts out your polynomial function. So when I'm talking about the lead coefficient, we should be familiar with that a value out front. Okay, the lead coefficient. So there's different notations for the right tail is up or the right tail is down. Okay, so if I'll just draw this, the axes here. Okay, this is something we have to get used to. The horizontal axis is the x-axis and the vertical axis is the y-axis. So if we're going to the right, okay, our numbers are positive, right? This would be like on the x-axis, this would be a positive 1, 2, 3, and so on. And as we're getting bigger, we're going to go into positive infinity. So when you see the positive infinity, it basically just means you're on the right side of the graph, or okay, and likewise on the other side, negative infinity is on the left side of the graph for the x-axis. Okay, similarly, on the y-axis, we have, as we're going up, we're going to have positive infinity. We're going toward positive infinity if the y's are going up, and we're going toward negative infinity as the y's are going down. All right, so basically there's a special notation that you'll see that talks about the right tail as being up. Okay, so if I were to draw this cubic graph, looks like a cubic graph, and I'm looking at just the right tail, okay? A way to tell that the right tail is up, the notation that displays that, we say as x is approaching positive infinity, okay, that just means as x is going to the right, if it's going up, that means the y value is approaching positive infinity, okay? So this notation, if you see this, it's basically telling you the right side, because x is going to positive infinity, is going up, all right? We can also write the right tail is down, okay? So we're still going to the right, so as x approaches positive infinity on the right, okay, in this case, the y value would be approaching negative infinity, it's going down. Okay, so the graph for this one might look something like, this. Okay, on the right side, the y value is going down. Okay, so we really, if we just start looking at these and talking about them, you'll get a better feel for this. So just by looking at this polynomial function, we want to focus on the highest exponent. Okay, so the highest exponent is a 3. We know that this has a special name. It's called a cubic function because the highest exponent is 3, and I'm just going to say x to the third. Okay, so since this 3 is an odd number, we know the tails will be opposite. Okay, and above I talk about the fundamental theorem of algebra, where the number of roots can be potentially the same number as the highest root. So it says how many roots does this function have? This function should have 3 roots. Now, not all of them have to be real, but since the highest exponent is 3, then we should have 3 roots. So this is called a third degree function because of the highest exponent being 3, and there are 3 roots. Okay, so the end behavior, we already talked about that the tails are going to be in opposite directions. But if we look at this a value, the lead coefficient, since the lead coefficient or the a value is positive 2, okay, that tells us about the right tail. Okay, since it's positive, the right tail is going to go up. All right, so we know the right tail is going up. And we know the tails are going to be opposite directions. So that means the left tail has to be going down. Okay, and I can look at this just by looking at the equation. Also, this number at the end, I should change my color to different. Okay, so this number at the end, the -2, the constant, it has no variable with it. Okay, this is going to be my x-intercept. Okay, so when let me do this. When x equals 0, okay, if I were to put a 0 in for all of my x's, okay, that would cancel all this first part out, and my y value would equal -2. So the coordinate 0, -2, okay, this is going to be my y-intercept. So this last number, the constant, is a y-intercept. All right, so now we're going to use a graphing tool to actually graph this. And when we're graphing it, we have to be very precise. So we're going to fill in the table with these specific points, and then we're going to actually add more points, and we actually call these points critical points. So we're going to fill in the chart, and then we're going to list some critical points. Okay, so before we graph this, just make sure you look at the scale. Okay, the scales are very important. And you'll see on the y-axis, it starts at 1 right here. So this is actually counting by 1, and actually this last value, whatever number they have here, goes to the last value. So there are 10 lines here. On the x-axis, Every line is 0.5, so this is 1, this is 2, this is 3, and so on. Okay, same in the negative direction on the x-axis. All right, so I already put this up on Desmos, and it gives us the domain, the x values they want us to use from -2 to 2. So when we go to Desmos, if you want to see the table, you just go to the settings and click table, and it actually gives us these numbers to plug in. So we're going to go back to our lab, and I have already had these written down. So it's -2, 6, -1, 3, this is -2, -9, and -6. All right, so we're going to plot these points first. So -2, remember this is -1, and this is -2, and then we count by ones on the y-axis, so 1, 2, 3, 4, 5, 6. There's our first point. -1, 3 is here, 0, -2, okay, 1, which is right here, -9 is 1 above the 10. Remember the -10 is actually right here. And then 2, -6. So this is 9, 8, 7, 6 would be right here. All right, so this graph, you can see our points. It really doesn't tell the whole story, so that's why we need to also add these what we call critical points. All right, so the critical points are the zeros, okay, or the roots. And on Desmos, these are very easy because we can just hover over them. Okay, they're also the x-intercepts. So I'm going to write these down. Negative 1.605. All right, so we have negative 1.6050. We also have, I guess I would just click on them, negative 2.263. Okay, and then there's one other 0. And this is 2.368. Okay, so we have 2.368, comma 0. All right, so besides the zeros, the other critical points are called the maxima or minima. Maxima or minima. And in this case, there is no absolute maxima or absolute minima because if we look at the graph, these should really have arrows on it. I can't write on this, but this graph keeps on going, the right tail keeps on going up into infinity, and same with the left tail, so there's no actual absolute minimum because it keeps going down, or absolute maximum, but there's what we call a relative max. Okay, this is our relative max, so -1, 3 is already on our chart. -1, 3 is a relative max, and this right here, 1 1/3 or 1.3 repeating, -907 is called a relative min. Okay, so the relative maxima, okay, and it's like a local maxima, is -1, 3, and for the relative minima, okay, it's not an absolute minimum, but it's just relative to that area. That was 1.3 repeating, comma, -9.704. All right, so like I said, we want to be very careful when we plot this. So we know that this -1, +3. Oh, that means I made a mistake. This point is wrong. It should be -2, -6. So I'm going to erase this one. And I have -2, -6. 1, 2, 3, 4, 5, 6. Okay, there's my point. So I'm going to make my points purple so I can see them. All right, so we have this picture so far, and none of our zeros are actually on the graph. So I'm going to graph my zeros. -1.6. So this is a half. Remember, this is 1. -1.6 is right about here a little bit. So there's a 0 right there. Negative, that's about a quarter, which is about halfway between 0 and -0.5. So there's another 0. And then, and obviously we can't be exact with these, so we just try our best. So 2.3 3, 6, 8. Well, this would be 2.5 in the middle between 2 and 3. So maybe about right here. Okay, so I can kind of connect my dots, and I want to kind of stick too close. I don't want to draw my extension too far from this because it could make my graph incorrect. All right, there's that. I'm going to round it right here. Right. Okay, oops, I forgot to plot my minima, so I'm going to do that before I go any further. So 1 1/3, and then I have to go down to about 9.7, so approximately here. Okay. And I'm going to go down, and I'm going to go up. I'm going to draw an arrow on both ends. Okay, so this is my graph, and you can see from the graph that my roots, as long as they cross the x-axis, they're real. So I have 3 real roots, and since it was a 3rd degree, that means none of my roots were imaginary because this is the maximum number of roots I can have. And since I can see them all visibly crossing the x-axis, that means I have 3 real roots. Okay, so 3 real roots, and that means I have 0 imaginary roots. All right, so there's another one of these graphs, okay, to practice. And again, just from looking at the equation, we can tell some properties. First of all, we have a positive lead coefficient, we have a degree of 4, and we have the y-intercept. So since we have a positive a value, oops, positive a, because that's a positive 2 is our lead coefficient, we know the right tail is going to be going up. All right, so, and it's a 4th degree. Oops, that's supposed to say 4th. Okay, it's 4th degree, which is an even number. So the tails are going to go in the same direction. So since the right tail is up, both tails are up. Okay, both tails are going to be up. There can be a potential of 4 roots. Okay, well, there are 4 roots, but 4 real roots, potential for 4 real roots. And the negative 16, remember, is our y-intercept. So we know 0, negative 16 is going to be our y-intercept. All right, so I can already fill in that 0, negative 16 without even typing it into Desmos because I can look at the graph. All right, so I am going to pause this so I can put this on Desmos. Actually, I want to show you how this is done in Desmos when you change it. So you can just hit the X and then you can start typing it in again. So we have y equals the 4th. So do 2x, shift 6 to the 4th, hit our arrow key to get out of there, and then minus 17x cubed. Shift 6. Oh, not yet. X. Oh, shift 6 cubed, and then plus 39x squared. Okay, minus 8x minus 16. Okay, and you can see, like I said, as the degree goes up, there's more curves, and you can see that both tails are up. We talked about that. All right, so now it's time to graph these. We want to go to our table, so we do settings, and we hit table. And in this case, it doesn't give us, it just stops at 2, and we have to go to 5, so we can just type in 3 and then hit enter, and then 4 and enter, and then 5 and enter, and that's all we need. So again, we're going to go back to the notes. All right, I have this copied down. It was negative 16, then 0, and then 20, 14, 0, and 44. All right, so again, we don't want just these points. We also need the critical points. Again, pay attention to the scale. Okay, now the y-axis counts by 2, notice. So every one of these lines is a 2, and the x-axis still goes by a half. So this is going to be 1, 2, 3, 4, 5. As for the y values, 2, 4, 6, 8, 10. I'm just going to mark 10 here. And on the bottom, I'm also going to mark negative 10. So 2, 4, 6, 8. This would be negative 10. All right, so 0, -16, that'd be 12, 14, 16, that would be right here. Just going to change color for my points. There's my first graph point. 2, so +2, and then up 20. 20 would be 1 down from the 22, which is really at the very top line. 3, 14, so we have 3 right here. There's 10, 12, 14. And then 4 is a 0. And then 5, 44, that's going to be off the chart. Okay, so I'm just going to just remember that at the end so my graph is kind of accurate. All right, in this case, if we look at this, we also have some zeros that aren't on the graph, okay? So if we look at this, there are the 4, 0 is actually a double root, okay? So this is considered to be a double root. And then we have a root here, -1/2 0 and 1 0. Okay, somehow I missed 1 0 on I'm plotting my points. So 1 0 and then -1/2 0. All right, so I have a critical point of -0.50. That is another 0. And I also have a relative, I'm just going to put R min, and a relative max that I need to add. Okay, so if I look at, the relative min is this lowest point on the graph. And there could be more than one relative min. We just have to look at where it curves. So this is 0.11 and then -1643. Okay, so we have -16.43. All right, and then let's see about those are relative min. The other relative min is the 0 of 4, which is already taken care of. And then we have a relative max of 2.265 and then 21.058. Okay, so 2.265 and 21.058. And again, we'll just get as close as we can. All right, so the -1/2 0 I already put on there. The min, that's just 0.1, so it's really close to the y-axis. And -16 is -20, -18. So it's just below the -16 y-intercept, so I'm just going to put it there. And the relative max is at about 2.25. So 1, 2, about halfway through here and up to 21. So just a little higher than this point. Okay, so I'm going to look at my graph again. Okay, it looks like a kind of like a W, a wacky W. So it goes infinitely high. We hit that relative minimum. We come back up to the middle. We bounce on the x-axis here at 4 and then go up. All right, so that's what I need to make my graph look like. So again, when I connect the dots, I'm going to kind of stay close to the leftmost point that I have to make my point accurate. I'm going to go down here, hit that lowest point. I'm going to come up here. I'm going to hit these points, hit my relative max. I'm going to come back down. It's going to hit the 4, and it's going to bounce back up. And remember, 5 was supposed to go to 44, so I'm just going to, again, I'm not going to draw my arrow too high, because if I cross this line, then my graph is inaccurate. So I just want to stay and graph at something like that. And it does look a little different than the calculator just because my scale is different. So that's why it kind of looks stretched out. All right, so there's my 4th degree. So like I said, be precise, make sure you get those critical points, and use your artistic abilities to graph. And we can see we were right. The right tail was up. Both tails were up because of that even degree. let's talk about this a little bit. There are 4 real roots, okay? Here, there's one distinct root, and when this happens, when we have this like bouncing I mentioned earlier, and it just touches the x-axis and goes back, this is called a double root, okay? So this is a double root. And it shows you down here that if we factored that polynomial, okay, if we factored this polynomial, it would actually turn into this. So we can actually tell the roots by finding the zeros. And it says it has a double root at x equals 4 because this root, we could really just write it twice if we really wanted to. And we find our zeros by just setting each factor equal to 0. So this one, -1, we'd subtract the 1 and then divide by 2. And you can see our -1/2 is right there. Okay, the 0 of this one would be x equals +1, which is our 0 right here. Okay, we should change the colors. So that was the -1/2 right here. This is the +1, and there's our double root at 4. So really all 4 roots, they're all real. Oops. But there's only 3 distinct roots because one's a double root. All right, exercise 3. Okay, so now this is a little different. They're going to give us a graph and we're going to answer the questions. All right, so if we're looking for the lead coefficient, well, we need to know what that the sign of that lead A value is. So we're going to look at the right tail. All right, so since the right tail is down, that means the lead coefficient must be negative, okay? And we knew that because the right tail is down. Oops, right tail down. All right, is it even or odd? Well, the tails are opposite. So since tails are opposite, we have an odd degree. All right, based on the number of turns, how many roots are possible? Well, we haven't talked about this yet, but the general rule is we look for the number of turns. So we don't count this the highest. So we're switching from going negative, and we switch to positive. So this is the turn, and I'm going to circle all my turns in pink. So here's a turn, and then I go positive, and then I'm switching to negative. So right here, here's another turn, and then I'm going negative to positive. Here's another turn, and then here's another turn. Since I have 1, 2, 3, 4 turns, okay, what I do, the general rule is I add 1. I always add 1 to the number of turns, and that gives me the number of the potential degree. So this looks like it might be a 5th degree. Okay, so the turns plus 1 will give you the degree. And likewise, you can do the degree minus 1. If you worked backward, the degree minus 1 equals the potential number of turns. Okay, this is just a general rule that works sometimes, not all the time. All right, so based on the maximum number of roots and the graph, how many are real and how many are imaginary? Well, since I only have 3 roots where it crosses the x-axis, I know that 3 are real. Therefore, it's looking like a 5th degree. 2 would have to be imaginary. And I mentioned earlier at the beginning that imaginary roots always come in pairs. So this always have to be, you always have to have an even number of imaginary roots, which it's working out for us. Okay. All right. One last question. Okay, we've already learned how to factor. It says factor completely, and that usually indicates that we can factor more than once. And I notice this is a difference of 2 perfect squares. So I'm going to first break it in to 4x squared minus 9 and 4x squared plus 9. And then this is also a difference of 2 perfect squares. So this is going to be 2x minus 3 and 2x plus 3. And then I'm going to get the 4x squared plus 9, which cannot factor because it's not the difference of 2 perfect squares, it's the sum of 2 perfect squares. So this is my factored completely form of my binomial. All right, so now Sarah's going to graph this, and she's saying that all the roots of this are real, and we have to determine if she's correct. So we can actually do this two ways. We're going to do it algebraically, and then I'm also going to show you this quickly graphically. So graphically, I'm just going to graph it and check it out. But first, we're going to do it algebraically. All right, so to find the roots of any polynomial function, we do it just like we did with quadratics. All right, we're going to set this equal to 0, and we're going to solve. Well, we already did the factored form above, so I'm just going to copy that. We said the factored form was 2x plus 3, 2x minus 3. It wasn't in this order above, but it doesn't matter. 4x squared plus 9 equals 0. And to find the roots algebraically, we just set all these equal to 0 and solve. So in this case, we're going to subtract 3 to get 2x equals negative 3 and divide by 2. So x equals negative 3 halves. That's a real number. So there's one real root. All right, and then we have 2x minus 3 equals 0. So it's going to be the same procedure, except we're going to add 3 first. So we're going to get 2x equals a positive 3. And then we're going to get a real root of 3 halves. Okay, so we have a negative 3 halves and a positive 3 halves, two real roots so far. When we set this guy equal to 0, I guess it kind of already, we can use that. I'll just rewrite it. Okay, so 4x squared plus 9 equals 0. I'm going to subtract 9 first. I'm going to get 4x squared equals negative 9. Okay, there's a couple different ways to do this. I could divide by 4 first, or I could take the square root of both sides now, since 4x squared is a perfect square. And I'm going to get 2x equals, well, there's my negative underneath the radical. Okay, if you remember, we dealt with this briefly in the beginning of the year. We take the negative out. That's an imaginary component, so it comes out as an I, and the square root of 9 is 3. So really, this is 3i, which indicates an imaginary number. And when I divide by 2, actually, I need to take a plus and minus with the square root, so I get x equals plus or minus 3i divided by 2. So this indicates I have a positive 3i over 2, which is imaginary. And I also have a negative 3i over 2, which is my other imaginary root. So in this case, I have 2 real and 2 imaginary. So is she correct? The answer is no. All right. And from my work showing here algebraically, 2 of the roots are real and 2 are imaginary. All right, so I'm going to do a quick graphically solution, a graphic solution to show you what it looks like. So I'm going to go to Desmos. I'm going to close that out. I'm going to type in y equals 16x to the 4th minus 81. All right, now this looks like 2 straight lines, but if I kind of zoom out, I see it's going to cross the x-axis. You can see that negative 1.5, that's my negative 3 halves. This is my positive 3 halves. And then if I zoom down, it kind of rounds out. There's my y-intercept at negative 81. And notice how the bottom is kind of a flatter version. So sometimes with fourth powers, they'll only have one turn, but it's going to be like a flatter turn. Okay, so it can be in higher power if it looks like a parabola with a flat bottom. Okay, this is an x to the 4th. So I'm just going to sketch this. So I'm going to make my scale so we can see this. I'm going to make this negative 81. And this is going to be, my x scale is obviously way different than my y scale, because this is going to be negative 3 halves, and it's going to be positive 3 halves. So basically my graph came down like this. It flattened out at the bottom, and it rounded up. Both tails were up. It's positive. It's a 4th degree. So the tails are in the same direction. And like I said, even though it's a fourth degree, it does not have to have 3 turns, okay? It can have just a flat bottom, which indicates more than one root there. So I have 2 real roots, and then I also, since I have 4 potential roots, I can tell that 2 are real and 2 are imaginary. So basically, if 2 are real, the other 2 have to be imaginary, and I can also tell that from my graph. All right, so like I said, your homework, you're going to submit these notes, and then you'll find another assignment. It's like just a real quick I think it's about 5-question assignment on Canvas that just checks for understanding of all of this information. So, see ya.